Hi there and welcome to another video from Hegarty Maths. It's Mr. Hegarty here. This is a Decision Maths A-Level video on linear programming, the 7th one. In this video we're going to solve a linear programming problem using the Vertex testing method. So we're going to do two examples in order to do that, and I'll explain what Vertex testing means as I do this. Now, one thing to point out is in video 6 I showed you how to solve a problem using the objective line method. For me, the Vertex testing method is always the best one. It's the easiest one for me. I would always do this if I'm not told which to do. Sometimes you're told which one you must do, but if I'm not told, I would always do this one. Okay, so here's a typical example. Say we're solving a linear programming problem. We're minimizing our objective function, which is this, subject to our constraints, which are these. So the first thing we're going to do, obviously, is we're going to plot all of our constraints, etc., to find our feasible region. So firstly, we're going to plot y is equal to x to represent this one here, and we're going to want below the line, and we're going to want a whole line because it's less than or equal to. So it goes through 0, 0, and it clearly goes through 20, 20, and we're going to make it a whole line, and we're going to make it red. Now we want y less than or equal to that, so we want below the line, so what we're going to do clearly is shade above the line. Okay, so we want everything below that area there. But I could just make it go on a bit further. Right, next one. Actually, while I'm here, let me just do the easy ones and tick off the easy ones. Let me do y bigger than or equal to 5. So we're going to draw y equals 5 here. And we want y bigger than or equal to 5. So we're going to get a line and we're going to draw it green at 5 here. Now it's a whole line, not a dotted line, because it's bigger than or equal to. And we want above the line, so we're going to clearly shade below the line. Okay, next one, x is less than or equal to 13. So let's do that one. So let's draw x is equal to 13 here. So, and it's going to be a whole line here, not a dotted line, because it's less than or equal to. So we draw 13 here, which is this point here. And what do we want? We want less than or equal to, so we're going to shade more than or equal, or more than on the diagram, that which we don't want. So we're going to shade this here. Okay, we've got our last constraint here, 3x plus 5y is equal to 60. Okay, so let's do that here. So we want to draw 3x, add 5y is equal to 60. Easiest way to do this is if you let x be 0, then 5y would be 60, so y must be 12. And the other way around, if you let y be 0, 3x would be 60, so x must be 20. And you plot those two, so plot 0 versus 12, and you plot 20 versus 0 there, and you draw yourself a line. That one there. Now you want above that line, so you're going to shade everything below that line, namely this. And we've determined here our feasible region. This here is our feasible region. So let me just mark the vertices of my feasible region. This one here I'm going to call A, this one here I'm going to call B, this one here I'm going to call C, and this one here I'm going to call D. Now, just imagine for a moment I drew the objective line up here. So say I wanted to draw this objective line. Now, the objective line is x plus 3y is equal to some constant. X plus 3y is equal to some constant. And I think, what number do 1 and 3 go into? That would fit nicely on the graph. I'm thinking 18. So let me draw x plus 3y is equal to 18. If you make x equal 0, then y would be 6. If you make y equal 0 even, then x would be equal to 18. Okay, so we're going to plot 18, 0 versus 0, 6. I'm going to put a line through it like this. Now, you know, when you're using the objective line method, you move this line up, keeping it parallel to how it started, and the answer, if it's a minimum, is always going to be the first vertex it enters into the feasible region, and if it was a maximum, it's going to be the last vertex as it leaves the region. So here it looks to me clearly that the answer is going to be equal to point C. Okay? Now the problem with that method is it requires me to draw the objective line. It's quite fiddly moving it around, and you're never quite sure if it, when it's a small diagram, it's hard to tell for sure which point it is. So forget now I even had that, but I'm thinking the answer is D. I always know the answer is going to be at a vertex. Okay, so the rule is that the answer to an LP problem is always, and just a little caveat, except in integer cases, which I'll do about in the last video, a vertex of your feasible region. So what a good method to do would be to find the coordinates of the feasible region, stick them all into your objective function, and see which one's smallest. Okay, so what we're going to do is we're going to say points A, B, C, and D. We're going to find those points by talking about the intersection of each line. So for point A, it's the intersection of red and black, so y equals x. So it's the intersection of y equals x, which I'm going to write as x take away y equals 0, and 3x plus 5y is 60, so 3x plus 5y equals 60. So it's the intersection of those two. For B, it's the intersection of x is 13 and y is x. So y equals x and x is equal to 13. For point C, it's the intersection of x is 13 and y is 5, so it's the intersection of y equals 5 and x equals 13. And for D, it's the intersection of 3x plus 5y is 60 and y is 5, so it's the intersection of y equals 5 and 3x plus 5y is 60. Okay, so we can find each of these by simultaneous equation. Now, some of them are easy. This one here, when x is 13 and y is x, that must mean that x and y are 13. So that coordinate there is clearly 13, 13. Where x is 13 and y is 5 intersect is clearly the coordinate 13, 5. Now here it tells you y is 5, so you can put that straight in here. So you would get 3x plus 25 is 60. So 3x must be equal to 60 subtract 25, and 60 subtract 25 is equal to 35, so x must be 35 over 3. So this one must be 35 over 3 and 5. And the last one here, you can do that by simple simultaneous equations. Alternatively, as I showed you in the previous video, you could use your calculator, do mode equation 5, and you've got 1x, negative 1y, and 0 with 3x, 5y, and 60, and they give the answer 15 over 2 and 15 over 2. So 15 over 2 and 15 over 2. Okay, just to have a double check they look right, they look about right. Okay, so they're each of the coordinates which we'd have to find, and now we want to minimize this. So what we do is we work out x plus 3y. For each of these sets of coordinates, and we work out which one's the minimum. So I'd get my calculator here, right, and I'd use that, I'd go here to, I'd type in x plus 3y. So what I do is 15, so what I do is I want to work out x plus 3y, so I type, my first number is 15 over 2 plus 3 times 15 over 2. And I'd work that out and I get 30. So here the objective is equal to 30. The next one I'd go back. I change that to 13. I get 52. I've now changed that to 13 and 5. So I just need to change this one to 5, get 28. And the last one I'll change to 5 again. And what's that? 35 over 3. And I get 80 over 3. And 80 over 3 is approximately 26. So it's 26.6 recurring. So which one's the minimum? Clearly this one's the minimum. Oh, maybe not. D's the minimum even. D's the minimum, sorry, because that was 26. The minimum here is here. Okay, and the question was to find the optimal value of the function. So the optimal value is 80 over 3 at point D, which is 35 over 3 and, sorry, 5, like that. And that's how you would do this type of question. One more example. You may want to pause the video and do this one yourself now. So we're going to firstly draw the feasible region for this set of inequalities here. So these are our constraints. And then we're going to maximize this objective function and minimize this for the same set of constraints. Okay, so each one I'm going to draw separately. Let's start off with the easy one. Let's draw y equals x, this one here. Okay, that's easy to draw. That goes through 0, 0, 5, 5, 10, 10, etc. So get a ruler and you just draw that there. We want below the line, so we shade everything above the line, and we want a full line, not a dotted line. So what we do, okay, done for the first bit. Then we've got to work through some of the harder ones. So we might as well start off at the most difficult. So 9x plus 11y is equal to 99. Clearly if x is equal to 0, 11y would be 99, so y would be 9. Or if y was equal to 0, x would have to be equal to 11. So we can plot 0 with 9, 0 against 9, with 11 against 0. Get a ruler. We want a full line because it's less than or equal to, and we want below the line, so we shade above the line. Okay, so next one, let's draw this one here. 4x plus y equals 28, so 4x plus y is equal to 28. So clearly if x was equal to 0, y would be 28, which is probably too big to fit in our graph here, so let me pick another one. Let me pick x. If x was equal to 2, then y would be equal to 20. That would just about fit. And if y was equal to 0, x would be equal to 28 divided by 4, and x would be equal to 7. Okay, so I can plot those. I can put 2 against 0, so sorry, 2 against 20, that should be 2 against 20, which would be here, and I can plot 7 against 0, which would be here. So that's how it would look, something like that. Now we want below the line, so we shade everything above the line. Now almost everything's above the line is being shaded apart from this here, so we need to shade that as well. Okay, and then what we need to draw is we need to draw 5x plus 3y is bigger than 30, so 5x plus 3y equals 30. So if x was 0, y was 10, and if y was 0, x must be 6. So 0, 10 gets plotted with 6, 0, which is here, straight line, like that. And let's just think what we want here. For that one, we want above the line, so we shade everything below the line. So we go back here to our highlighter and we make sure we shade everything below the line here. Okay, so at the moment we've got a feasible region that looks something like that. Last one we need is x plus 2y is equal to 8. So we have x plus 2y is equal to 8. So clearly, if x is 0, y is 4, and if y is 0, x is 8. So we plot 0 against 4, which is here, and we plot, we plot 0 against 4, 0 against 4, which is here, and we plot 8 with 0, which is here, and we draw a line in like that. And looking there, we want above that line, so we shade everything below that line. Okay, so we shade this. So this ends up turning out, this here turns out to be our feasible region. And we know by vertex testing that that point, that point, that point, that point, or that point is going to be our answer. So that maybe A, B, C, D, or E is going to be our answer for a maximizing or minimizing a problem. So what we need to go on and do is we need to find A, B, C, and D. So let's do a table. So let's write the vertex here. So let's write A, B, C, D, and E. And let's write what meets at those points. So at A, the orange meets the green. So at A, 5x plus 3y equals 30 meets the green, which is y equals x, which I'm going to write actually as x subtract y equals 0. Okay, at B, what meets? The red meets the green, so the red is 9x plus 11y equals 99. And I'm going to write the green again as x take away y equals 0. So I can use my calculator. For C, the blue meets the red. Okay, so that's going to happen at the following. That's going to happen where 9x plus 11y is going to be equal to the blue, which is 4x plus y is 28. So 4x plus y is equal to 28. Okay, D occurs where the turquoise meets the blue, so that's where 4x plus y equals 28 meets the turquoise line, x plus 2y is 8, so x add 2y is equal to 8. And the last one is where the orange meets the turquoise, so 5x plus 3y is 30, so 5x plus 3y is equal to 30, meets the turquoise, which is x plus 2y is 8. Now, in order to find those coordinates, which is the first step you need to solve all of these simultaneously, okay? Which you can obviously go and do. However, you'll notice I did something when I wrote these down. I wrote them with the x first, in all of the cases with the x first, you see? And with the y second, the number of y's second, and what they're equal to, what constant they're equal to, the other side of the equal sign. The reason I did that is I want to be able to use the calculator to help me do these questions a little quicker or check in an exam. So what I can do is, the first thing I want to work out is the coordinates of each of the vertices. So I'm going to write a heading down for the coordinates, calculator out. Remember, I've showed you this in a previous video, so mode equation number 1, and we type 5, 3, 30, 1, negative 1, 0. 5, 3, 30, 1, negative 1, and 0. And we get 15 over 4 and 15 over 4 for the coordinates. So our coordinates are 15 over 4 and 15 over 4 for A. Okay, for B, what's it going to be? Well, we want 9, 11, and 99, and 1, negative 1, and 0. Okay, so keep the 1, negative 1, 0, and change that to 9, 11, 99. Press equals 99 over 20 and 99 over 20. So 99 over 20 and 99 over 20. Okay, for C, we want 9, 11, 99 and 4, 1, 28. So keep the top row. Okay, keep the top row there, and we want 4, 1, 28, and we get the answer there, 209 over 35 and 144 over 35. So 209 over 35 and 144 over 35. Okay, the next one, you want 4, 1, 28. So you want the 4, 1 and 28, and you want 1, 2 and 8. So I'm going to put 1, 2 and 8 along the top. Press equals, you get 48 over 7 for this one here. So you get 48 over 7 and 4 over 7. So and 4 over 7. So 48 over 7 and 4 over 7. Okay, the next one, you want 5, 3 and 30, and you want the 1, 2 and 8. So you want the 1, 2 and 8 keep, and you want 5, 3 and 30. 36 over 7 and 10 over 7. So 36 over 7 and 10 over 7. Okay, there we go. They're all our coordinates as follows. Okay, now what we want to do is we want to maximize or minimize two different objective functions. So we want to maximize this and we want to minimize this. So what I'm going to do is I'm going to have two headings, one for each one. So we want to max x plus y, and we want to minimize 3x plus 4y. 3x plus 4y. So what we're going to do is we're going to work out these for each of these cases here, and we're going to see which one's the maximum and which one's the minimum. Okay, so for the first one, we want to maximize these, so we want to add together 15 over 4 twice, so 15 over 4, add another 15 over 4, well we clearly know what that's going to be 15 over 2. Okay, so this is 15 over 2, which is 7.5. I rounded it, I decimalised it just so I can get a rough feel for how big the number is. The next one we're going to add these two, so 99 over 20, add another one of those, so basically timesing it by 2. Oh, my fault, 99 over 20, come out of that and multiply by 2. I get myself 99 over 10, which is clearly 9.9. Okay, the next one, I'm going to add these two together, which is going to be 209 plus 144, all of that, 35 over 35. So I get from my answer there 353 over 35, 353 over 35, which is 10.1, roughly 10.1. The next one, I add these two, so 48 over 7 plus 4 over 7, which is going to be 52 over 7, and 52 over 7 is about 7.4. And the last one, I add those together, and I'm going to get 46 over 7. So I'm going to get 46 over 7, which is 6.75. So 46 over 7, which is equal to 6.75. So my minimum is going to, so if I want a maximum here, the maximum out of these ones is clearly this one here. So the maximum here is going to happen there, which I'll discuss at the end about writing it down, how you write it down. And let's do the minimum for each of these. So we want 3 of those and 4 of those. So it's just a case of typing the answers in here. So we do 3 multiplied by 15 over 4 plus 4 multiplied by 15 over 4, and I get 105 over 4, so 105 over 4, which is, as a decimal, 26.25, so 26.25. So I go back here and I want the same thing, other than I swap these fractions here with 99 over 20. Swap this over here, 99 over 20, 693 over 20, 693 over 20, which gives me 34.65, so 34.65. Okay, next one, I want to put in here 3 lots of x. Okay, and x was 209 over 35. And I want 4 lots of y, and y is 144 over 35. And I get 1203 over 35. So I get 1203 over 35, which is about 34.37. Okay, the next one I want to swap with 48 over 7. With 4 over 7, 160 over 7, 160 over 7, which is about 22 odd. And the last one, I would change that with 36 over 7 and 10 over 7. So delete 10 over 7 there, and 36 over 7 there, and I get 148 over 7, 148 over 7, which is approximately 21.1. Okay, so we've got, these are the answers. Now we want to minimize this, and the minimum happens if we look at this last one here. So the minimum is going to happen at E. Let's state our final answers for each of the parts A and B. We wanted to find a maximum of x add y, and that occurred at C, which was the coordinates 209 and 35, 144 and 35, with value, this here, 353 over 35, which if you write as a mixed number, so we have 353 over 35. If you want to write it as mixed, you just press that, and 10, the answer would be 10 and 3 35ths. And for part B, we wanted the minimum of, what was it, 3x plus 4y, so it was 3x plus 4y. It occurred at E, which had coordinates 36 over 7 and 10 over 7, and the value was 148 over 7, which you can write as a number, as a mixed number, 148 over 7. You can write that as 21 and 1/7, so 21 and 1/7. And that's it. That is a solution to this problem. To both of these, we've maximized this, we've minimized this, and we've used the Vertex testing method. So hopefully you found that useful, and now you can do these style of questions. So thanks loads for watching.